You know, in every car, there's a battle being fought every single second. But it's not measured in miles or kilometers, it's measured in milliseconds. Today, we're going under the hood to witness one of the most critical conflicts of all, the alternator's constant, invisible fight for electrical stability.
Think about it. It's a simple, familiar action. You get in the car, you flip on the headlights, crank the AC, maybe turn up the radio, and in that moment, you've just issued a massive command for power. And in that tiny fraction of a second, your alternator, well, it's literally fighting to keep the entire electrical system alive. A complex electromagnetic drama begins to unfold, a drama that decides whether your car's electronic heart keeps beating. So, to really understand this fight, we have to look at the battlefield itself. Let's dive into the instant of demand, this invisible electromagnetic battle. And here it is. This is the heart of the machine. You have a spinning part, the rotor, which creates a magnetic field. And then you have these stationary coils around it, the stator, and that's what actually generates the voltage from that spinning field. The basic idea is simple, right? More speed or a stronger magnetic field means you get more voltage. But it's the in-practice part where things get really complex.
Okay, so the moment you ask for power, the current that starts flowing through those stator coils creates its own magnetic field. And this is the crux of the problem. This is called armature reaction, and it's basically a direct counterforce. It pushes back against the rotor, actively weakening its main magnetic field, and that causes the voltage to dip. You could say, this is the villain of our story.
This whole battle, it unfolds in 3 distinct acts, and it's all over in less than a second. First, there's the subtransient phase. In the first 10 milliseconds, the machine's own internal physics, they kind of absorb the initial shock. Then, we enter the transient phase. This is where the magnetic fields really start to fight each other, and the voltage dip hits its absolute lowest point. And finally, steady state. This is when the system's commander steps in and stability starts to return.
But what about the opposite problem? What happens when a large load suddenly disconnects? All that stored magnetic energy, it has nowhere to go. And it erupts in a massive voltage spike. On a normal 12-volt system, that spike can exceed 40 volts. That's more than enough to fry sensitive electronics. This is what's known as a load dump, and it's incredibly dangerous.
So, the system is under attack from both sides, voltage dips and these massive voltage spikes. How does it possibly fight back? Well, it has a hero, and that hero is the voltage regulator, a tiny electronic brain with a very powerful strategy for a counterattack.
Its number one weapon is something called field forcing. Here's how it works. The moment a big voltage dip is detected, the regulator just overrides everything. It abandons all finesse. It immediately drives the field winding to 100% power, basically slamming the accelerator to the floor. The goal is simple. Raise the field current and therefore the magnetic field as fast as physically possible to force that voltage back up.
But you know, modern systems have an even smarter trick up their sleeve. It's like the alternator gets a phone call warning before the load even connects. Through a communication network, it's called a LIN bus, the car's main computer can literally tell the alternator, hey, get ready, a big load is coming. This lets it start building up its magnetic field before the hit. The result? The voltage might not even dip at all.
Of course, this battle isn't being fought in some perfect, clean laboratory. No, the real world presents a whole gauntlet of complications, things that push the system right to its absolute limits.
And this is where you run into a fascinating paradox. At idle speeds, say 1800 RPM, the alternator is spinning slowly. It's weak. There's not much magnetic flux, not much torque to spare. This is the real danger zone, where a big load could cause a total voltage collapse. But then, at highway speeds, maybe 10,000 RPM or more, the problem completely flips on its head. Now it's spinning so fast it's generating too much voltage, and the fight is all about stopping the system from overpowering and damaging itself.
And then, you have the great enemy of all electronics, heat. At a typical operating temperature, let's say 150 degrees Celsius, the resistance of the copper field winding goes up by a massive 51%. 51%, think about that. It severely chokes the regulator's ability to push current to the rotor, which basically weakens its main weapon right when it needs it most.
So, let's put it all together. Picture this. It's a scorching hot day. You're stuck in traffic, fully loaded. The AC is blasting, the radiator fans are running full tilt, and your engine is just sitting there at idle. This is the absolute worst-case scenario that engineers have to design for. This is the moment when all of your margins are at their absolute thinnest.
Okay, so when you're faced with these unforgiving laws of physics, how on earth do engineers design a system that can win this fight, not just once, but every single time?
With physics itself fighting against them, how do engineers guarantee a stable voltage? Well, the answer isn't some single magic bullet. It's actually a series of incredibly careful, balanced trade-offs, where every single design decision has a real consequence.
Let's look at 3 of the biggest trade-offs. First up, the drive belt ratio. You can make it spin the alternator faster to get better output at idle, but then you risk overspeeding it and causing huge mechanical stress on the highway. Tough choice. Then there's the rectifier. Do you use standard, cheaper diodes, or do you go for high-efficiency synchronous rectifiers that cost more but waste way less energy as heat? And finally, you have to manage all the electronic noise from the system. All that high-frequency switching has to be filtered out so it doesn't mess with your radio.
And that rectifier choice, it's more important than you might think. We're talking about a lot of energy. At full load, old-school diodes can waste more than 100 watts of power, just turning it into pure destructive heat. Think about a 100-watt light bulb. That's a lot of heat to deal with under the hood. Modern synchronous rectifiers can save almost all of that, making the whole system way more efficient.
So when you look at all this, you realize an alternator isn't just a simple generator. It's really a sophisticated, self-regulating power plant, working right at the heart of the modern vehicle.
And its performance is governed by an incredibly strict set of rules. The voltage dip can't be more than 1.5 volts for a 50-amp load step. The recovery time has to be less than 300 milliseconds. That load dump over voltage, it has to survive that 40-volt spike. See, these aren't just abstract numbers on a spec sheet. These are the hard and fast rules that keep all the sensitive electronics in your car from getting fried.
And maybe the most incredible part of all of this entire epic battle, from the initial voltage dip to the regulator's fierce response, all the way to stabilization. The whole thing happens silently, invisibly, in less time than it takes you to blink.
Which leaves us with one final, forward-looking question. As cars continue to evolve, moving towards more powerful 48-volt mild hybrid systems, how will this invisible battle change? The stakes are only going to get higher, and the fight is about to become even more intense.